A very good afternoon to you all, and welcome to the session. So this is the sixth lecture in the series. So till now we have discussed about how do we read and write different raster formats. So today we will discuss about like once after reading an image, like suppose if you wish to do some kind of processing on that image. So basically we will discuss about how do we do some geometric transformation on an image. Then we will talk about some intensity transformation, then some morphological transformation and spatial filtering on the images, right? So till now we had just seen how do we read and write the images. Now we will see how do we manipulate our image, right? So manipulating the image so that it meets a certain application depending on some applications might be useful for enhancing the visualization of image. Some operations might be able to remove some noise from the image. So so we'll discuss about enhancing or transforming the image. Like we will apply some transformation on the pixels of an image so that that image becomes more useful for some particular application, right? So for this, anyway, I will be using a combination of Opencv and GDAL. So GDAL, anyway, we have already known. So I will introduce you another library called Opencv that actually can read and write images as well. But plus, actually, it is one of the most common used or versatile library used for computer vision applications. So basically, we'll talk about geometric transformation, intensity transformation, morphological transformation if possible, and then some special filtering on the images. And so, if we just recall what an image is, or more precisely, a digital image, what is digital image? A digital or raster image is represented, as we discussed that in multiple lectures. A digital or raster image is represented as an array of real numbers, right? So, if you can see that in in image, x and y axis are used to denote the rows and column numbers that are referred as that we said that can be referred as its pixel number, line number, and pixel number, right? So all these values, these all are pixels, and this may be f x y. If we say that function f that represents the intensity of that pixel, right? So x and y represents its maybe line number and pixel number. So any digital image can be represented as a two-dimensional or three-dimensional matrix of like this. There you can say that the pixel intensity is determined by this function f. So now these all are pixels. Now we will define something called neighbors of a pixel, right? So suppose this is our pixel. So there can be multiple neighbors of this image. So in one instance we can say that these two pixels on the same line number are the neighbors of this, or we can specify these two also might be its neighbors. So these are two neighbors. Then that two diagonal pixels also can be the neighbors, or these can be neighbors of a pixel, or these all 8 pixels can be called the neighbors of the pixel. So depending on which kind of application we are referring to, so these are the different neighbors of these pixels. These can be these 4 pixels or these four corner pixels, right? So these we call two neighbors, four neighbors, or 8 neighbors of a specified pixel, right? Now let us talk about spatial operation. Actually, one of the spatial operations we have already seen that was we were calling it local operation of single pixel operation. So spatial operations are performed directly on the pixel of an image, right? So suppose if you wish to manipulate the values of our values of pixels in our image, so spatial operations are being performed directly on the pixel of every pixel of everywhere depending on that. So special operations are the operations that are directly performed on the pixel of an image. There are other kind of operations. Those are called frequency domain operations, right? So those are those are applied on the Fourier transform of an image, or say in the frequency domain. So special operations are performed directly on the pixel of an image. Special operations uh, generally can be broadly categorized into three categories. Right, one what we call single pixel operations or single operation. That example we have already seen. Then other kind of operation, special operation is called neighborhood operations or focal operation. Or then third type of operation which can we apply, that is called geometric spatial transformations. So what is single pixel operation? The value in the output image is determined by the specified operation on the pixel in an input image, right? The simplest operation we perform on a digital image is to alter the intensity of its pixels individually, right? So a single pixel operation means the value of pixel in an output image is determined by some specified operations on on a pixel in a single image, or maybe suppose there some operations might involve more than one images, like we may apply the same operation on the pixels of more than one image. So the value of the pixel in output image is determined by a specified operation on pixel in an input image. So the simplest operation that we perform in digital image to alter the intensity of its pixel individually using some transformation function, right? Maybe it may be multiplication, scaling by some number or something like. Suppose if you have to apply, if you are applying this transformation t on the input image z, so that will be calling single pixel operation. So this operation will be performed on the every individual pixel, right? So now, for example, we have seen already like ndvia and ndw that. So we were applying this nir minus red divided by nir plus red on every pixel of our image. The second kind of operation is called neighborhood operation. So the value of pixel in output image is determined by a specified operation on the neighborhood of a pixel in the input image, right? So in case of single pixel operation, the intensity in the output image was based on just on a single input image, right? So we were applying some certain mathematical operation on single input pixel. But in case of neighborhood pixel, the value of the pixel in output is determined by a specified operation on neighborhood pixels of an input image. So here we will not be the output will not just be based on the single pixel in our input image. So it will be based on the we will be applying an operation on the entire neighborhood of a pixel, right? So depending on, maybe we may choose to apply it on the two neighbors, or maybe 8 neighbors, 4 neighbors, depending on what kind of application we are doing, right? So in this case, the value in the output so this was the our xy pixel in our input image, then this output of xy pixel in our output image will be the output of some operation on the all pixels in the neighborhood of this xy pixel, right? So like here you can say that it may be like, suppose if you are taking this pixel, so when we apply certain operation on all 8 neighbor of this pixel, so we maybe it may be an average of this entire area, or maybe maximum, minimum, or some other mathematical operation on this entire neighborhood. So whatever output comes, that output will be assigned to the center pixel of it. Like 21 will be replaced in the output image as by the value 18.7. So right, so that may be an average or maximum, minimum, or whatever operation we are applying, right? So in single pixel operation, the value of output pixel is determined just by an single input pixel. But in case of neighborhood operations, the output is of the output we get the output by applying certain operation on the its entire neighborhood, right? So then third kind of spatial transformation is called geometric transformation. So these all geometric transformation modify the spatial arrangements of pixel in an image. So till now whatever we were applying those, they were not altering the spatial arrangement of the pixel. So geometric transformation is an operation that modifies the spatial arrangements of a pixel itself. Like we may change their locations itself, and not just intensity, we may just change their locations as well. So these transformations are called rubber sheet transformation, because they can be viewed as analogous to printing an image on a rubber sheet, then stretching, shrinking, or sheet according to the predefined set of rules, right? So in geometric transformation, we are just changing the spatial arrangements of the pixels as well, not just their intensity values. We are changing their spatial arrangement as well. Like this, maybe like scaling an image, or stretching an image, shearing, transforming, So these are images are operations are called geometric transformation, where we are just modifying its, where we are not just modifying the intensity values, we are modifying their spatial arrangements as well. So any geometric transformation can be expressed as a matrix. Like suppose this was our x and y was our original location of our pixel, right? So we will be applying some transformation on that transformation called t on that xy vector. So then we will be getting new location of that pixel in new image. Maybe that might become x dash comma y dash, right? So then this transformation can be represented as a matrix T of four elements T11, T12, T21, and T21, T22. Right. So some example of transformation, like suppose x dash y dash is suppose x by 2 comma y by 2. That means we are shrinking the original image to the half of its size, right? In both spatial direction, in x and y direction, we are, if we wish to shrink the original image to by half, so that is one kind of geometric transformation. It is possible to use, like, then there are different kinds of geometric transformation, like scaling, translation, rotation, or shearing. Then it is possible to use a homogeneous matrix to express all these operations with a single matrix, right? But they only their coefficients are going to vary depending on what kind of operation we are doing. So these all operation, like operations of scaling, translation, rotation, and shearing, can be represented as a matrix of 3 cross 3. Like, so these all will be the elements of that, and one we are adding one more row with values 0 0 1 and xy1. So with this we can perform any of these operations of scaling, translation, or rotation. So what is scaling? Scaling is just a resizing of the image, right? So the transformation moves the coordinates of pixel of an image to a new location. So scaling is just, we just wish to resize our image, maybe halving the just we want to make the pixel size 1 by 2, or maybe just want to double it to fill the entire screen on, and so on. So plus the, so when we are scaling an image, so we need to calculate the values of pixel intensity in new location, right? Suppose if you are stretching our image, or reducing or contracting the image, then what happens, there will be new locations we will be getting, like, so on on these new location, for these new location we need to calculate new intensity values. So the new intensity values need to be assigned to these new locations. So this is the new intensity values are calculated using something called intensity interpolation. So there are most few common interpolation techniques are nearest neighbor, bilinear, or bicubic interpolation. So in case of nearest neighbor assigns to each new location the intensity of its nearest neighbor in the original image, right? So the new, well, suppose if you are getting a new location in our transformed image, then the value in the new location is assigned to the intensity of location assigns to each new location the intensity of its nearest neighbor in the original image. So similarly, there are bilinear interpolation. It uses the four nearest neighbor to estimate the intensity at a given new location, right? So the intensity value in a new location will be calculated based on the four nearest neighbor in the original image. Similarly, in case of bicubic interpolation, it uses 16 nearest neighbor to estimate the intensity at a given location. Right now, for doing all these operations, we will be using a versatile library named Opencv. So Opencv, they say Opencv is the world's biggest computer vision library. Opencv is open source and it contains over 2,500 algorithms and is operated by some non-profit open source foundation. Right, OpenCV is an open source library that includes several hundreds of computer vision algorithms. OpenCV provides tools for image processing. Till now, GDAL, whatever, as we said, that GDAL is just a library for reading and writing vector and data formats, right? So once you read an image using GDAL, then you get a NumPy array. Now, suppose if you wish to do some image processing operations on that NumPy array, actually GDAL doesn't provide those operations. So either you can write your own functions, or you can use OpenCV library for doing those image processing tasks, right? So OpenCV supports multiple programming languages including C++, Python, Java, and MATLAB. OpenCV also is being widely used in various fields such as robotics, augmented reality, facial recognition, medical imaging, autonomous vehicles, and there are many more areas where it is being used. Now let us see, suppose if you wish to do this geometrical transformation of scaling on an image, right? Scaling, as we have discussed already, that scaling is just resizing of the image. So OpenCV comes with a function called cv.resize. So this resizing can be done using GDAL as well, but right now we will be using OpenCV. So OpenCV comes with, because we are doing many other thing as well. So OpenCV comes with a function called cv.resize for this purpose. Right, the size of image can be specified manually, or we can specify a scaling factor. Right, so either we can specify, okay, if for original image of 100 by 100 cross 100. Suppose if you wish to modify it to say 50 by 50 or 25 by 50, we can specify both of these to cv.resize. Either we can specify new size of the image, or we can specify in terms of scaling, like half of that, just half, make it half, or whatever it is. Then we can specify, as we said, that because once we are resizing an image, there will be new pixel locations. For those pixel location, we need to calculate new values using interpolation. Like there are different ways of interpolating new values on those new locations. So we can specify which interpolation technique to be used as well, like inter area, for intercubic or interlinear, whatever can you specify while doing the for interpolation, right? So for first thing, first we need to install OpenCV to our system, that as I have just installed. So for installing the single command we can use, in first activate your environment and conda install -c conda 4, then OpenCV. So once you do OpenCV, install it, OpenCV gets installed to your system. Then the name of the package is, or module is CV2. So CV2 I am just importing as CV, and other things remain same as well, right? Whatever we were using, matplotlib we will be using for plotting, and GDAL, and even OpenCV also we can use directly for reading an image, but I will be using the combination of GDAL and OpenCV. Right, so first I am changing my working directory to the directory where the data is available, and I will be reading this band4.tif image, so that I'll be using all geometric transformation or intensity transformation on this particular image. Right, as usual, I am just opening the file for reading, and img.read as array, if I specify, it is just reading that image. So ds.read as array will give us a numpy array. Right, now suppose if you wish to resize that image, right, so cv.resize, then we can specify it, our image, and you can specify these other parameters, like suppose if you want to specify fx and fy. So if you wish to read about this function, then we can say cv.zd. Then here you can specify our original image, and by what size, like scale factor. See, these are their scale factors, 0.1 and 0.2. Suppose if you want to reduce the image size by 10%, then interpolation, with interpolation to use for, like suppose if you wish to use the cubic bicubic interpolation, then cv.intercubic. If I do this, then here now if I see these images, like original image is in img, and the rescaled image in rescaled image. So if I see there, now you can see that originally the image was of something around 2000 cross 15 cross 1500 cross, right? Now we have reduced the image size by 10, so 10%. So we have specified the scaling factor to be 0.1 by 0.1 by 0. So we have just reduced the image size to 1 by 10. Right, so now you can see that in the output image, the size of output image is almost in x direction it is 150, in y direction it is almost 175, and you can see the image got distorted. This was our original image, and this is our rescaled image. Similar way, suppose if you used to stretch the image like then you can specify these fx and fy to be one, two, twice, thrice, four times, or whatever you, right? So now the second operation is translation. So translation is the shifting of an object's location. Suppose if you wish to uh, translate, like if you wish to move the image from one location to, like, all pixels, suppose if you wish to move in x direction, say 50 by 50 50 pixels in the x direction and maybe 30 in the y direction, right? So for that we can specify translation is the shifting of an object. If you know the shift in x and y direction, then it can be, like as we said, that all these scaling translation can be specified using a single matrix. So for this, numpy has a function. Sorry, numpy, I am saying that Opencv has a function. For that, we need to specify a matrix like this. First we need to specify these four parameters, like in a matrix called 1001, and tx and ty are our new x and new y's. Like suppose if I want to move the image, say no movement in the x direction, but I want to move 500 by 500 pixels in the y direction, then I need to specify the matrix like this. Now if I see this m, so m is like this, right? So in the x we have said that zero movement, and suppose if you want to just move the image in y direction, right? So then we can just call this function cv dot wrap affine and specify it our original image, then our matrix, and number of rows and columns. So now if you see this image, these two images together, so this was our original image, and we have not moved it in x direction, but we have moved in y direction, right? So this way we can translate the image, like shift the location of pixels in our image. Similar way, suppose if you wish to rotate the image, for rotating an image, we need to specify a matrix like this, cos theta, sin theta. Suppose whatever where rotation of an image for an angle theta is achieved by a transformation matrix like this, then we can just specify this transformation matrix by calling this function cv dot get rotation matrix 2D. Then you can specify it like this. Then here you can specify our angle, and this will be our matrix. Then similar thing, wrap affine, if we call on that image, that rotates the image by the specified angle. Then if you see this was our original image, and this is the rotated image, right? Only thing that this way we need to specify a matrix, and by calling this function cv dot get a rotation matrix 2D. So this gets this rotation matrix for us, this which Opencv will be using internally, and rotate the image like this. You can rotate the image. So this was our rotation angle. So this was all about a geometrical transformation. Now we will talk about image intensity transformation, or say image enhancement. So the term spatial domain refers to the image plane itself, and the image processing method in this category are basically based on the, as we said, that are based directly on the manipulation of the pixels of an image. So there is another way where we can specify, modify, or do some operations on the image, that what we call frequency domain. So here in the frequency domain, instead of directly operating on the instead of directly manipulating the values of pixels in an image, so we will first calculate the Fourier transform of the image, and the operations will be performed on the Fourier transform of them. That what we call the frequency domain operations. So as we said that there are two principal categories of spatial processing. One is spatial intensity transformation, and another is called spatial filtering. So intensity transformation operates on the single pixels of an image for a task such as contrast manipulation or maybe image thresholding. So basically most of the image intensity transformation functions operate on a single pixel. So they are all single pixel operations, and spatial filtering performs operation on the neighborhood of every pixel in an image. So generally intensity transformation are done on every individual pixel, and spatial filtering is performed on the neighborhood of pixel. So both of these fall under the category of say image intensity transformation. So in these both of these cases, we are just manipulating the uh, intensity of the image to so that the output image is useful for certain application. So we will be defining one term called contrast. So contrast in an image is defined as the difference in luminance or color that makes an object indistinguishable from the other objects within the same field of view. Right. So it is the difference in the luminance or color that makes the objects in an image indistinguishable from the other objects within the same field of view. Right. So essentially, it is the range between the, you can say that range between the brightest and darkest pixel parts of an image. So that's what we call the contrast of an image. So now we'll talking about enhancement. So enhancement is the process of manipulating an image so that result is more suitable than the original image for a specific application. The word specific is important because it establishes at the outset that enhancement techniques are problem oriented. Thus, for example, a method that is quite useful for enhancing X-ray image may not be best approach for infrared images, right? So when an image is processed for visual interpretation, ultimately the viewer is ultimate judge of how well the particular method works. So whatever image enhancement techniques we will be talking, basically they are dependent on how a user perceives the output. So ultimately the user is the ultimate decider of how, a decision maker of how good that particular enhancement technique is there, right? And different enhancement technique will be useful for different kind of applications or depending different so regardless of the application or method used, image enhancement is one of the most visually appealing areas of the image processing, like depending on for what kind of application you are doing that image enhancement. So as people say, as we say that image enhancement is one of the most visually appealing areas of the image processing, that you will see right there. So first I will see basic intensity transformation. So intensity transformations are among the simplest of all image processing techniques, right? So intensity transformation is the most simple of the all image processing techniques. So there are three basic types of function used frequently in image processing. So basically, one is called linear, negative, and identity transformation. So first intensity transformation is called, we will be applying some linear operation on all pixels in our input image. So then second, there are other kind of operation called logarithmic, log and inverse log transformation. They are non-linear operations. We will see with an example. Then or we can apply power law, right? So on every pixel intensity, we will apply some power form, do some power. So nth power or nth root transformation. So linear may be negative or identity transformation. Logarithmic, we can apply log or inverse log on pixels on our image, or power law. We can apply we can make intensity power to something. Right. So first, let us see a linear transformation called. We'll see then image negative. The negative of an image with intensity level range 0 to L minus 1 is obtained by using the negative transformation function. Right. Suppose if you assume that there are L intensity levels in our image. So with image negative, what we will be doing, we will be converting zeros, zeros which were brightest in our image. Suppose zeros we want to convert to the maximum, and wherever level L or highest level we want to convert to zeros, right? So the transformation can be applied by L minus 1 minus R, or L minus 1 minus, or you can say simply you can say L minus R. R is our intensity in our original image, right? So if the original image intensity, if it was 0, so in the new image or in negative image, it will become L, highest, and wherever is for highest in the original image L, so it will become 0. So all the brighter parts will become darker, and darker parts will become brighter. Reversing the intensity level of a digital image in this manner produces the equivalent of a photographic negative, you can say, right? So this type of processing is generally used, for example, enhancing white or gray details embedded in dark region of an image. So suppose there are some features or gray details embedded in some dark or white region of an image, so which are generally not visible, right? So if you make the negative of an image, so they will become quite clearly visible, right? Especially when black areas are dominant in size. When there are most black areas dominant in our size, then if we do the negative of that image, so the small areas will become whiter, right? Now let us see with an example how do we do that. So anyway, we have seen this negative transformation in the previous lecture as well, but now we'll try to see it within Opencv. Now same thing, I have just opened the file for reading. So ds.read as array that I read. Now suppose if by calling img.max, I get what is the maximum intensity level, right? So in my image, the maximum intensity level is 306, right? So in the negative image, what I will be doing, L minus img. So 306 minus, if I subtract every pixel from 306 from the max pixel, or I can say even -1 also I can say. So it will make the negative of that image, right? Now if you see both these two images together, so now you can say actually this has become almost dark. So if I try with some band 2, so here you can say at least I think it was not quite clearly visible, but or I can apply the formula np dot invert, so that also might be. Right, so this way you can see that because I think that was an unsigned integer, because of that this negative operation had not. So now this you can say that this is a negative of an image. All the areas which were white, black has become white, and white areas has become black, right? So this is one of the linear intensity transformation on an our image, right? So the second kind of transformation what we can do for image enhancement is called log transformation, right? So if R is if R is the intensity in our original image, then if we apply this formula C, so, log 1 plus R. So we take the log of input pixel and we multiply it by some constant, so that we call log transformation. Right, so this is how do we apply log image is equal to, suppose if I am taking the C as 1, np dot log of 1 plus image, right? So that applies the log transformation of the image. If you see that image, now you can say that the contrast of image has slightly improved, right? If you see the image between these, difference between these two, so this was almost all dark. So in this, the darker areas has become slightly more visible, right? Slightly the by using the log transformation, we have slightly improved the visualization of image. Then there is another call, as we said, that power law or gamma transformation, right? So in this case, we apply the pixel intensity in the output image is calculated as C multiplied by R raised to the power gamma. So R is our intensity in our input image and gamma is some constant what we are talking. So if you know about power law curves with fractional values of gamma map, so if you are taking the gamma as a fractional value less than say fractional values, or say fractional values less than 1, then power law curves with fractional values of gamma map a narrow range of dark input values to a wider range of output values. If you see in your image that some areas are very dark, right? So that if you apply if you apply a fractional values of gamma, like gamma less than 1, in that case what will happen, these values in the small range in the darker side will be expanded to the to a wider range in the output values, right? So with that we will see slightly improved contrast if you have images very dark areas. So if you apply the power law transformation with gamma less than 1, like with some fractional value of gamma, so in that case you will see that the darker areas, the small pixel intensities in the small range of pixel intensities will be mapped to the wider range, right? So suppose this we if we apply the function like np dot clause. Now I am applying in our original image np dot power img and power 0.01, gamma less than 1. Now if you see, this was our original image and slightly improved version, right? So if I increase the gamma maybe 0.02 or 0.5, then slightly more. So there, this whatever areas was completely dark, they have stretched out, their dynamic range has quietly stretched out and they look a bit better compared to this. Right, so this is another example of this. You will see that gamma transformation. So here I have a washed out image, like where the pixel intensity is in the. So this is the image, original image looks like this. So here you can see that the pixel has saturated, right? So now what we need to contract the high range, higher values, higher intensity values, right? So because it looks like the image has a washed out appearance, like the so if we can contrast the contract the very saturated values together, so if for that we can use the gamma of greater than 1. In that case, what will happen, the intensity in the high range will be just stretched out. So in washed out appearance, indicating that the compression of intensity level is required, right? So for that we can use different gamma levels. So one, suppose if you use gamma 3, 4 or 5, so we can use 3 combinations. So power image 3, np original data, we are doing to the power 3 and power 4 and power 5, and with this we will see that how does the appearance of the image changes. Right, now if I see these all images together, so here you can see slightly the contrast of the image. This was our original image, and here we have used the gamma value of 3, right? So where we are trying to compress the high intensity values. So if we use gamma equal to 3, where we are doing like output, we are calculating using this formula C r to the power gamma. So if you use gamma, because in this case we need to compress the high intensity values. So for that, if you see, so here the images have slightly improved, like as we increase the value of gamma, the appearance of the image is changing. So this was our original image, and by changing this, applying this power law transformation with the value of gamma 3, 4 and 5, we see get these images. So then we'll talk about thresholding. So thresholding is also a digital image processing digital image processing technique used to segment images by converting grayscale images into binary images. Like suppose if you wish to convert a grayscale image into binary image, like suppose if you just want to convert your image to a map containing just water bodies into your image, right? This process involves setting a threshold value and classifying each pixel based on whether its intensity is above or below its threshold. So for every pixel, like in the thresholding technique, what we'll do, we'll just select a threshold and all the pixels above certain threshold will be assigned value, say 1 or maybe 255, or all the pixels, all pixels with value beyond that or less than that threshold will be assigned value, say 0. Right. So in this case, for every pixel, the same threshold value is applied. So if the pixel value is smaller than or equal to the threshold, it is set to 0. Otherwise, it might be set to a maximum value. At this one already we have seen, like suppose if you wish to calculate the NDWI of your image. So the formula for NDWI is green minus NIR divided by green plus NIR. So I have just read these two images and try to calculate the NDWI. Right. So this is an image. Now suppose in this image, if you wish to convert to a grayscale image, so for that we need to choose a threshold. Right. Suppose if you want that all the pixels above, say threshold of 0.2 should be assigned the value to 55, and all the pixels which has value less than threshold of 0.2 will be assigned value 0. For that, CV2 has a function called CV.threshold. So if you call CV.threshold and pass it your numpy array and the value of threshold, like 0.1. So all the values above 0.1 will be assigned the value 255, and all the values below 255 will be assigned the value below 0.1, sorry, will be assigned the value 0. Right. Then what kind of thresholding technique to use? CV dot threshold binary. Then it returns two things. One is our returned image and the threshold value. So now if you see both of these images together, in the previous case, like in the last lecture, we have used the function called np.where for doing this thresholding. Otherwise, if you wish cv2 thresholding also you can use. Like here you can see that this was our original image and this is the binary image converted to this. So all the pixels above 0.1 has been assigned the value 255, or they are looking quite brighter in an image, and all other areas have become dark. Right, so this way we can do the segmentation on your image. So contrast stretching is also another technique, image enhancement technique. So low contrast images can result from, like we might get, so this image intensity transformation can be used for, there is another way for improving the visualization of image, that what we call contrast stretching. So low contrast images can result from poor illumination, or maybe say lack of dynamic range in the imaging sensor, or even the wrong settings of the lens aperture during the image acquisition. So contrast stretching expands the range of intensity level in an image so that it spans the full intensity range of the recording medium or display device. Like so, when if you see in contrast a histogram of your a poor contrast image, you will see that the your histogram of the image will be centered around certain value, right? So if we stretch the pixel intensity values to the entire range or entire dynamic range, full intensity range of the recording medium or display device, it improves the visualization of the image. Let we will see with an example how do we do that. So one of the ways we can just clip, suppose this is our original image, and so you can see that the contrast of image is not so good. So if we plot the histogram of this image, so matplotlib has a function called plt.hist. So there we can pass our image and specify like in how many parts you want to show. So this is the histogram of an image. You can see that most of the pixel, though the even if you are representing it as 8-bit, so pixel intensities or can range from 0 to 256, but most of the values are lying in the 350 plus minus maybe plus minus some 10 or 20, right? So with contrast stretching we can change we can change the intensity value such that this occupies the entire range of intensity values from 0 to 256. So for that we can use this, you can apply the formula called, so stretch image can be like if we calculate IMG, the whatever pixel value minus minimum value available in that pixel multiplied by 255 divided by max value minus min value. If you apply this, so all pixel values will be scaled in the range 0 to 256. Right, now if I see this histogram of this stretched image, now you can see that it is taking the entire range from 0 to 256. So now if I see the image, so you can we can see the by contrast stretching we can improve slightly improve the, so this image enhancement technique might not be useful on all images, right? So there is another technique for contrast, improving the contrast is called histogram equalization. So histogram equalization produces a transformation function that seeks to generate an output image with uniform histogram, right? So if you generally see as we have seen that if you see the histogram of a poorly image with poor contrast, you will see that the histogram is centralized around certain, is occupying just a small range in an image, right? So with the help of histogram equalization, we can spread the histogram to the entire range of intensity values. So consider an image whose pixel values are confined to some specific range of values. For example, a brighter image will have will have all pixels confined to high values, but a good image will have pixels from the all regions of the image. So we need to stretch this histogram to either end, right? So that the histogram equalization does whatever does this. This normally improves the contrast of the image. So in a poorly contrasted image, the histogram will look like this. So with the help of histogram equalization, we'll try to transform this image to the histogram of this image from this kind to this kind. So this that's for OpenCV has directly functions for doing this histogram equalization. Anyway, this is I've just read the image. So if I see the histogram of this image, so I have calculated the histogram of that image. Now if I see the hist, so these are the values. If you plot anyway, we'll see with the plot. Later on for in the histogram equalization, what do we do? First, we calculate the cumulative histogram from that, right? So histogram has a function called hist.cumulative sum. So that will calculate the cumulative sum of all these values. Like this histogram is giving, if I see this hist, so this gives the values like with pixel intensity, with intensity 0, there are 2 pixels. With pixel intensity 1, there are 9 pixels. 108, there are 108 pixels with pixel intensity 3, right? So now we will first calculate the cumulative sum of the cumulative histogram from this, right? So 0, then every value will be the sum of previous two values. So 1 will be 11, 108 plus 9, 117. Like this, we will be keep on adding. Then we will be normalizing this. So hist dot cumulative sum calculates a CDF from that, and we are normalizing this. Now if you see the cumulative histogram, so this is the cumulative histogram, and this was the original histogram of our image. So that is centered around us. It is occupying a small range in our entire range. So once we calculate the cumulative histogram of an image, then we can apply this formula CDF into V minus CDF min divided by M cross N minus CDF min cross L minus 1, where L is the number of levels in our image, right? So if you apply this formula, this calculates the new intensity value for all our pixels. Then if we calculate this, so now if we see the image, and if we see now this way, by applying the cumulative histogram equalization, we can see that the is improved. The contrast of the image got improved to great extent, right? So this is the way how do we do the histogram equalization using OpenCV. So now we'll talk about this. These all the techniques for doing the intensity transformation. Now we'll talk about spatial filtering. So the name filter is borrowed from the frequency domain processing, where filtering refers to passing, modifying, or rejecting some specified frequency components of an image. For example, a filter that passes low frequencies is called a low pass filter. The net effect produced by a low pass filter is to smooth an image, right? In image, if image by blurring it. So we can accomplish the similar smoothing directly on the image itself by using these spatial filters. So spatial filtering modifies an image by replacing the value of each pixel by a function of values of the pixel on its neighbors. So till now, whatever intensity transformation techniques we have discussed, so they were all based on the value of a single pixel. So spatial filtering is based on, in case of spatial filtering, a new value is calculated from all its neighbors, right? So suppose this is our image, so we will be sliding a kernel of say size 3 by 3 or 5 by 5 over these all entire images, like suppose if you want to calculate all 3 cross 3 neighborhood, right? So we'll be sliding a kernel of this size over all these images, and it will be calculating the values of all these pixels across the way. So first we will talk about some called smoothing spatial filters. So smoothing also is called averaging. Spatial filters are used to reduce sharp transitions in the intensity. Right? Smoothing is there are very sharp transition in our image. So with the help of these smoothing filters, we can reduce this sharp transition in our image, so that some random noise can be suppressed using this. So because random noise typically consists of sharp transition in intensity, an obvious application of smoothing is to for noise reduction. So spatial filtering consists of a convolution of convolving an image with a filter kernel. So we will be uh, convolving the entire image with a filter. So convolving a smoothing kernel with an image blurs the image with the degree of blurring being determined by the size of the kernel and the value of its coefficient. So they will determine how smooth the output image will be. In addition to being useful in countless applications of image processing, low pass filters are fundamental in the sense that other important filters, including sharpening, that what we call high pass filter or band pass or band reject filters, are also can be derived from these low pass filters. And so Opencv provides a function called cv.filter2d to convolve a kernel with an image. For example, suppose if you wish to create a kernel of like this, we'll see. So here I have an image, which has some noise in it. So we will try to smoothen that image using different spatial filtering. So one of the first thing is, suppose if you take an filter like this, right? So first I am reading an image. So first here we are creating a kernel np.1's 5x5, right? So we are creating a kernel of 5x5, and suppose this we want to create a kernel of that like this. So 1/2, 1 by with these coefficients. So initial 1 on all and 1/25 of all these pixels if you wish to do. So kernel we are creating here np.1's 5x5. So it creates a matrix of 5x5, and we are dividing it by 25. So that creates a kernel of this kind, right? So as we said that OpenCV has a function called cv.filter2d. So we need to pass it the arguments of our original image and the kernel, right? So if you pass cv.filter2d and kernel, so it does this convolution operation on all these images and produces the image, right? So this will be our blurred image. So now if you see, this was our original image containing some noise in this here, you can say, and by just doing a simple convolution filtering of with the kernel of size 5x5, you can see that the noise has been slightly suppressed, like the image has slightly smoothened. Even here you can see that in these areas this image got slightly smoothened. Right, suppose similarly, suppose if you wish to do some Gaussian blurring on your image, in this method, instead of a box filter, a Gaussian kernel can be used. So instead of having a box filter, we can use a Gaussian kernel. It is done with the function cv.Gaussian blur. So cv.Gaussian blur can be used for Gaussian blurring an image. So that also can be used for suppressing noise in our image. So we should specify the width and height of the kernel, which should be positive and odd, right? So the one case of normal kernel also, this a size of the kernel should be odd. We should also specify the standard deviation in x and y direction, sigma x and sigma y respectively. If only sigma x is specified, sigma y is taken as same as sigma x. If both are given as 0, they are calculated from the kernel size. So Gaussian blurring is highly effective in removing. If your image contains Gaussian noise, then you can use Gaussian blurring technique for removing Gaussian noise from your image, right? So for Gaussian blurring, as we said that cv.Gaussian blur and our data, then you need to specify the size of our kernel. Then if you want to specify sigma x and sigma y, both you can specify. Otherwise, if you specify 0, so both will be calculated from the Gaussian kernel itself, right? So blur, this is a blurred image, cv.Gaussian blur and our original data, and so you can see that the image is improved. So there is another kind of filter called median blurring. So the function cv.median blur takes the median of all pixels under the kernel area, right? So these so first pixel was taking an average and second was applying an Gaussian kernel. Suppose if you take the median of all pixels coming under the kernel, so the new value of output intensity of the new pixel is calculated by as the median of all pixels coming under that kernel, right? So the function cv.median blur takes the median of all pixels under the kernel area, and the central element is replaced with the median value, right? So instead of similarly, you can take average, like the first case was we were taking the average of the entire kernel area. So instead of average, suppose if you take the median, that is called median blurring filter, right? So this is highly effective against a salt and pepper noise in an image. So interestingly, in the above filters, the central element is newly calculated value, which may be pixel value in the image or a new value in the median. So, but so in that what we said in the previous cases. But in case of median blurring, the central element is always replaced by some pixel value in the image, because we are taking the median of the entire kernel area. Because if you see in case of average or other things, so in case of average, the pixel value was getting replaced maybe by the a completely new value, or it might come maybe existing in a new value. But in case of median, whatever new value for the pixel location we are calculating, that is will always be the from the original image, right? So it reduces the noise effect. Its kernel size should be a positive and odd integer, as we have done in the previous cases as well. Right, so this is our original data. Suppose now if you see, this was our original area, and you can see that there is, so this is the area of C, but there are so many salt and pepper kind of noise in this image. So if you do the median, if you apply the median filter on this image, then you will see that this image gets smoothened out, right? So for that, the function is in OpenCV has the function called cv dot median blur, and pass it the your original image and your kernel size. So kernel size, I suppose if I say 11 by 11, 12 by 12, sorry, it should be an odd number, 11 by 11 or 13 by 13, 3 by 3 or whatever. So this is our median image. Now if I plot these two images together, so data is our original data and median is our smoothened image. Now if we see this image, now you can see that this all salt and pepper kind of noise had got removed, and we see the nice filtered image. So like so for removing these kind of image, we can say that this median filter is quite effective. So with that, we come to the end of lecture. So I will just quickly summarize. So in today's lecture, we discussed about how do we manipulate the pixel intensities in an image so that the output image is more suitable for certain applications. As we said that there can be two kinds of enhancement or operations we can apply on an image. One is called these operations can be applied on either maybe say spatial domain, where we are directly modifying the intensity value of an pixel. So that is called a spatial domain. Or we can apply these enhancement techniques or transformation techniques even on the frequency domain, where we will be modifying the we'll be applying these operations say on the Fourier transform of an image, right? So then we will define the neighbor of a pixel, then we define different kind of operations on an image, say intensity transformation or spatial filtering. So in case of intensity transformation, the output pixel out the value in the output pixel was just being it was the output of an mathematical or algebraic operation on a single input pixel, right? So in case of but in case of spatial transformation, the output value was the result of operation on it, the entire neighborhood of a pixel, not just on a single pixel, right? So then we discuss about different image enhancement techniques like log transformation, linear transformation, or say power transformation, contrast stretching, histogram equalization, for improving the contrast of an image. Then in the last part, we discussed about different spatial filtering techniques, like so one of spatial filtering like average filtering or Gaussian blurring or median blurring, right? So with that, we come to the end of the lecture. So thank you very much for attending. If you have any questions, you may please paste them on the chat box. So thank you very much. We will be back after 5 minutes.